Hello everybody. How are you?
Good.
Ready for some fun?
Yes. Good.
Perfect. So let's talk about unique identifiers as primary keys. Who is using them as primary keys? Nice. You will hate me after that session. Hopefully you are not hating me. Few words about my person. My name is Klaus Aschenbrenner. I'm an independent SQL Server consultant. I'm only working with the relational engine of SQL Server, so I have no idea about business intelligence, data warehousing, just the relational engine of SQL Server. Sounds very, very easy. Is a very, very hard job. I'm also a Microsoft Certified Master for SQL Server 2008, which was the highest technical certification that you could have been achieved. I'm saying was, because Microsoft just retired that certification because they made no profit with it. Crazy story. I've also written the book Pro SQL Server 2008 Service Broker, which was published in the summer of 2008 by Apress. Service Broker is an asynchronous messaging framework that was first introduced back with SQL Server 2005, where you can also write very, very scalable database applications. Who is using Service Broker? One person. As you can see, I'm working with things that nobody cares about. So I'm really, really happy that you are using unique identifiers as primary keys. You can also follow me on Twitter. Here's my Twitter handle. Further information about my person you can find on my homepage at sqlbastion.ad, which is in English, not German. I'm also providing the so-called SQL Bastion Academy, where you are just finding free content, videos, weblog postings about various topics of SQL Server. What's the agenda for the next 90 minutes? Very simple. I want to convince you that GUIDs as primary keys are just a crazy idea. You will understand afterwards why. My background is .NET developer. So everything that I'm showing you, I have also done that. Okay? So I've also done all those mistakes, and I want to show you why in some cases a unique identifier as primary key is a bad idea. So I've also done all those things, so I'm not better than you. I was also just a developer working together with SQL Server. In the first step, as a prerequisite, I want to talk a little bit about clustered indexes. What is a clustered index? Why we need to care about clustered indexes when we are talking about primary keys in SQL Server. Afterwards, we move on to non-clustered indexes in SQL Server. As we will see, both indexes have a very, very strong dependency in SQL Server through the so-called clustered key. And afterwards, after we have laid out the foundation, we're just talking about unique identifiers, GUIDs, as primary keys in SQL Server. So I just want to show you why the default approach that is chosen by SQL Server is a bad idea. As we will see later, there's another approach within SQL Server where we can also use unique identifiers as primary keys, and it doesn't matter. SQL Server is just choosing by default a wrong approach. And if time permits, I will also show you afterwards why unique identifiers are perfect. Okay? So I'm a really crazy person. The first step I'm telling you, unique identifiers as primary keys are a bad thing, and afterwards I'm just telling you they are great. How does this sound to you? Good agenda? Perfect. We can't change nothing here. So let's start in the first step about the clustered index. When we are creating a primary key in SQL Server creates in the back for us a clustered index. Very, very important to know is that the primary key and the clustered index are just two different things within SQL Server. A primary key constraint is only telling SQL Server that we want to have unique values in a specific column, nothing more. It's just a constraint on our database table. We're just telling SQL Server we want to have unique values within that column. And SQL Server enforces that primary key constraint by creating a unique clustered index on our table. That's very, very important. As we will see later, we can also enforce a primary key constraint through a unique non-clustered index. But by default, SQL Server creates a unique clustered index on our table. When we are creating our primary key, means we have to talk in the first step about clustered indexes. A clustered index itself is just a so-called B-tree structure. A balanced tree means we have a root node with a navigation structure, and on the bottom we have the so-called leaf level where SQL Server is storing our data. It's the same concept as a phone book. In the phone book we have a sorting order, and in a clustered index we also have a sorting order, and the sorting order depends on our clustered key column. In our case, the column on which we are defining our primary key. So for example, when we are creating a primary key on an int identity column, we are just physically sorting our table by that int identity column. 1 comes before 2, before 3, 4, 5, and so on. Means when we are using a unique identifier as a primary key column, we are physically sorting our data by our unique identifiers. A comes for AA, comes for AAB, comes for B, for C, for D, for F, and so on. Okay? So as you can see in a clustered index, in the so-called leaf level, at the bottom, we have our data spread across so-called data pages. A page in SQL Server is always 8 kilobyte large. And above the leaf level, we have the so-called navigation structure, which we are using to find our records in the leaf level very, very fast. So when we are using the navigation structure for finding records in the leaf level, we are performing an index-seek operation in our execution plan. When we are just scanning the data page by page in the leaf level, it's a scan operator in our execution plan. Clustered index scan. Let's have a look on that. I'm creating here a new database. And I'm creating here a simple table. As you can see, I have a customer ID, it's a unique identifier, and in the next step, I'm creating a unique clustered index on that column customer ID. So for example, when you're specifying directly here the primary key constraint, we are also getting the same unique clustered index in the background. Okay, so SQL Server by default just enforces the primary key constraint for a unique clustered index. So I'm just creating here my unique clustered index manually. The next step, I'm inserting 80,000 records. Takes around 25 to 30 seconds. And afterwards, we're just analyzing that clustered index a little bit in detail. So I want to show you how those index pages looks like in the navigation structure and how the data pages in the leaf level looks like. So we're finished, 22 seconds. So when we're doing a complete scan of that table, we have in our execution plan the clustered index scan. Means we're just scanning the whole leaf level page by page. When we are restricting for a specific customer ID, just grabbing one here, we have in the execution plan a clustered index seek operation, means we are seeking for a specific record. It's the same when you're going to the phone book and you're searching for a specific person, for example, Maya. Okay? Very, very efficient because we have sorted our phone book on last name, first name. Here we can also make a seek because we have sorted our table physically on the column customer ID. So we can use the navigation structure of the clustered index to find that specific record. We can use the dynamic management function systemdb index physical stats to retrieve additional information about our index. As you can see, when we query for our customers table, in the detailed mode, we're getting back 3 records, means our index, our clustered index, consists of 3 levels. So we have an index root level, 1 intermediate level, and the leaf level with our data pages. So you can see the page count. We have 1 index root page, 28 pages in the intermediate level, and 5,852 pages in the leaf level where we are storing our data. And you can also see here the so-called fragmentation. The fragmentation tells us how much fragmentation we have in our index. Means when we have a very high fragmentation and you are accessing the table, for example through a scan operator, this leads to random I/O on traditional hard drives. As you can see here, we are dealing with a unique identifier. We have a fragmentation of almost 100%. Very, very bad. That's the first disadvantage of using a unique clustered index, of using a unique identifier as clustered key. We just have a very, very high fragmentation. Microsoft recommends rebuilding indexes when we have more than 30%. We've just inserted 80,000 records, 22 seconds, 99% fragmentation in the leaf level of our clustered index. So not very good. Next step, I'm creating a simple helper table. And I'm using the dbcc int command to retrieve all the pages of that clustered index. And what I'm doing here, I'm using the insert into statement to just write the output into the helper table that I have created earlier. Means we are now able to query those pages. For example, a page type of 2 are all our index pages. So we have 29 index pages here. We have all our data pages with the page type of 1 in the leaf level, 5,852. And now I'm just querying from an index root page. As we have seen earlier, we have just 1 index root page where a clustered index seek operation starts. So we have here a page ID of 628. And what I'm doing now, I'm enabling the trace flag 3604, and I'm dumping out that index root page with the dbcc page command. Means when we are doing an index seek operation in our execution plan, the first thing that SQL Server is internally doing, we're just reading our index root page. It's the first page that we need. As you can see here, we have here our primary key column, our customer ID. It's just a unique identifier. Means the unique identifier is 16 bytes long. Means we have here a huge overhead in the navigation structure of our clustered index. A page, index page, is again 8 kilobytes large. Means the larger our clustered key value is, the less records we can store on one index page. Means our navigation structure of the clustered index gets larger and larger and larger. And the navigation structure of the index is just overhead, nothing more. Overhead to find in a very, very efficient way the records in our leaf level. But we are not storing any useful information in the navigation structure. So for example, we can take a child page ID, dump that page ID out, and jump just one level into that clustered index. So we are now in the second level. We take another page ID and dump and jump to the leaf level, and in the leaf level we're just finding our data page where we have stored our records. That's a simple index seek operation. As you can see, we just need 3 page reads to find one specific record out of the 80,000. Doesn't matter which record, because it's a balanced tree. The way from the top to the bottom is always the same. In case when we are inserting new rows, SQL Server just rebalances that balanced tree. Okay? Make sense? Questions? Not yet. So let's move on. Let's talk in the next step about non-clustered indexes. A non-clustered index in SQL Server is just a secondary index. Imagine you have a book, for example a SQL language reference, and in the back of the book you have an index where you're searching for a specific command. That's a non-clustered index, a secondary index that you can define on different additional columns within our table. The non-clustered index, again, is a B tree, a balanced tree. So again, we have one index root page, multiple intermediate levels, and finally, again, a leaf level. And in the leaf level, we're not storing any data, because the data is stored in our clustered index. Means SQL Server is pointing in the leaf level to our data rows which are stored on data pages. Which pointer is SQL Server using here? Our clustered key. Means when we're creating our clustered key on a unique identifier column, we are also replicating that unique identifier in every non-clustered index on that table. Just imagine that. We're just polluting every index on that specific table with our unique identifier. Means we have a larger clustered index, and we also have larger non-clustered indexes. So again, we have our index level, our root level, multiple intermediate levels, and finally the intermediate level points to the corresponding record through the clustered key. In our case, through the unique identifier. Okay? Means our clustered key, our primary key, is the most redundant data in our table. Because we have that clustered key in every non-clustered index. Okay? What do you think about that? Good? Bad? It's not really good. Just think about that. We're creating a primary key constraint on a unique identifier. We are sorting our clustered index on that specific column. And finally, we are creating additional non-clustered indexes on that table. And we're just polluting every additional non-clustered index, again, with that clustered key. In our case, with the unique identifier. Most important thing is, when we are creating indexes in SQL Server, every index must be internally unique. Means we need unique values. When we create, for example, a clustered index, we can also create a non-unique clustered index. Means in that case, SQL Server internally adds a 4-byte long internal hidden column called the Uniqueidentifier, which just makes duplicate values again unique. Means we are getting again 4 bytes of additional overhead for our clustered key. And non-clustered indexes can be also created as unique and non-unique. What's the common case? Non-unique. For example, you have multiple customers in a specific country or city. This means SQL Server has to make those non-unique values in our non-clustered index again unique. What do you think what SQL Server is using here? To guarantee uniqueness in the non-clustered index. The clustered key in the leaf in the navigation structure means when you are creating a non-unique, non-clustered index, I also have to think a little bit. Non-unique, non-clustered index. When you're creating a non-unique, non-clustered index on a table where your clustered key is a GUID, a unique identifier, you also have that unique identifier in the navigation structure of that non-unique, non-clustered index. Means we are just polluting our whole non-clustered index with that GUID column. Means we need a huge amount of additional storage or space, which is stored in the storage and also in the buffer pool, in the in-memory cache of SQL Server. Just think about that. Let's have a look on a concrete example. Imagine we have a clustered key which is 100 bytes long. Just a very huge clustered key. Imagine you are clustering your table on first name and last name. And afterwards you see first name and last name is not unique and you are adding a social security number. So let's imagine we have a clustered key with 100 bytes. We define 15 non-clustered indexes on that table and we have 1 million of records. In that case we need 1.4 gigabytes of storage for those non-clustered indexes. Just because we have to store that very, very wide clustered key in every non-clustered. When we are using an int identity column, just 4 bytes, we need only 57 megabytes for storing the same amount of data and index again with 15 additional non-clustered indexes. Just think about that. And normally when you are using a larger clustered key like a unique identifier, you are doing it in every table, not just in one table. So we have a very, very strong dependency between our clustered index and our non-clustered indexes through that clustered key column. This means also when we are changing that clustered key, we also have to change all our non-clustered indexes. So a good clustered key should have 3 properties. It should be unique, like an int identity or unique identifier. It should be narrow, very, very small. Unique identifier 16 bytes, int identity 4 bytes. And it should be static, means it should not change. Okay? And of course, when we are talking about primary keys, that primary key is also a foreign key in our other tables. Means we're talking about our whole database schema. So you don't want to change that afterwards. Because in that case, you have to touch every table in your database schema. Okay? Let's have a look on non-clustered indexes and how we can make bad ones. Creating here again a new table. Again, I'm using for the first column customer ID a unique identifier. And what I'm creating in the next step is a non-unique clustered index. Means we can have duplicate values in the column customer ID. By default, when we are using the primary key constraint, we are getting a unique clustered index. So I'm creating here a non-unique clustered index. Okay? I just want to show you a really, really terrible example. So we have a non-unique clustered index. Again, I'm inserting 80,000 records. Takes again around 20 to 25 seconds. And afterwards, we are creating a non-unique, non-clustered index. So what we are getting is a non-unique, non-clustered index defined on a non-unique clustered index. Can you repeat that? Non-unique, non-clustered index defined on a non-unique clustered index. Very simple. Okay? So just a very, very bad example. So again, when we do a simple select star against that table, we again have a scan in our execution plan, and we create our non-unique, non-clustered index. Again, I'm creating a simple helper table, the same as previously, and we write all those pages into that table. And now we are again retrieving our index root page with a page ID 6258, and we dump that page out. And now let's see what we get back from SQL Server. We have our indexed column. Means our column customer name. We've defined a non-unique, non-clustered index. Means we can have duplicate values in that column. We have said an index, a B-tree needs unique values internally, otherwise you can't make it seek. You can't decide if you should go to the left or right branch. In that case, SQL Server must make sure that those values are unique. So what SQL Server is doing, SQL Server adds our clustered key. In our case, our unique identifier. So we get 16 additional bytes on overhead. Of course, we have told SQL Server we have created a non-unique clustered index. Means both columns are not unique. Means SQL Server has to add that uniqueifier. Means we have additional 4 bytes of overhead. Means our index record on our non-unique, non-clustered index defined on a non-unique clustered index is now 20 additional bytes long. And as you can see, you have now that unique identifier in every index record of every non-clustered index in that table. Do you like that? No. We don't like that. Just think about that, what we are doing. We're just polluting every non-unique, non-clustered index with that clustered key. In our case, with the unique identifier. Okay? And normally when you are creating a non-clustered index, normally it's a non-unique. Means we have the clustered key also in the leaf level of the, also in the navigation structure of the non-clustered index. Okay? So one problem just leads to another problem. Because by default, the primary key is enforced for a unique clustered index in SQL Server. Okay? So that should be the main outcome of that session. Just think about that the next time when you're creating a unique identifier. I'm just polluting every non-clustered index with it. Navigation structure and also in the leaf level. At least we have that clustered key as a logical pointer in the leaf level. If we are dealing with non-unique, non-clustered indexes, we also have the clustered key in our whole navigation structure. So even when we are jumping one level down, we're in the second level, and you can see again, we have our clustered key. And finally, when we jump down, we are in the leaf level, and here we have now just the logical pointer to the details of that record which was stored in the clustered index. Okay? So a bad clustered key also influences the design, the internal design, and the performance of every non-clustered index. Okay? So what are best practices? Not to use a unique identifier as clustered key, because we are getting a huge overhead in every non-clustered index. Means our non-clustered index just gets larger. We need more space in our physical storage. We also need more space in the buffer pool of SQL Server. So again, we are just polluting the in-memory cache of SQL Server with our unique identifiers. So a very good solution is a 4-byte integer value, like an int identity column. It's ever increasing, it's not changeable, and very, very small. Imagine what happens when we are dealing with a unique identifier. We have so-called page splits. I just want to demonstrate that on the flip chart, what a page split is. Imagine we have our clustered index. So we have said we have our navigation structure, and we are pointing here to some rows. And in the leaf level, we have our records sorted by the unique identifier. So we have our A's, B's, C, F's, FA, FP, 1, 2, 5, and 7. Imagine we are generating a new unique identifier, and we are getting a value of, let's say, t. We want to insert a new value of t. Where that value belongs to? Between C and F. Here. Do we have space? No. So what SQL Server has to do, SQL Server has to perform a so-called page split. Page splits are very, very expensive regarding the operations that we have to do internally, and they are leading to a very high fragmentation. As we have seen earlier, 99%. Means we are allocating somewhere else in our data file a new page, and that page is logically here. Means every page is a page ID. 80, 81, 82, 83, 84. Now imagine we are allocating a new page ID of 200. Means when we are scanning that index, we are scanning 81, 82, and afterwards we have to go forward to 200 in our storage. We are reading page 200, and afterwards we have to go back and read 83, 84, 85. It's random I/O in our storage. Very, very slow. Means fragmentation, external fragmentation means the logical sorting order of our data is not the same as the physical sorting order anymore. When we are dealing with unique identifiers, we always have 99% of fragmentation. Means every page is just out of order. We're just doing random I/O in our storage, which again hurts our performance when we are doing scans of that index. And also when we are doing insert operations because of those page splits. Page splits are very, very expensive. Very, very expensive regarding the transaction log. So let's talk now a little bit more about primary keys and how we can still use unique identifier values as primary key values. It's possible without all those various side effects that we have seen so far. First important thing, as I've already said, a primary key has nothing to do with a clustered index. A primary key is just a constraint on our table which tells SQL Server that we want to have unique values in that specific column. Nothing more. And SQL Server is using by default a unique clustered index to enforce that uniqueness. Okay? So those are just two different concepts. Okay? So a unique clustered index is just a helper method to enforce the uniqueness of that specific column. The nice thing is that uniqueness can be also enforced through a unique non-clustered index, through a secondary index. Means we can physically sort our table on different columns. So when you are creating a primary key with the primary key constraint, you can define primary key clustered or non-clustered. Clustered is the default option, means we don't have to specify it. So what are the advantages? We've already said they are not sequential, means we're just getting random values and SQL Server has to sort in the leaf level of the clustered index those random values. Means when we have no space on that specific location, we have to perform a page split. And page splits are very, very important and very, very expensive within SQL Server, as we will see later. We have a very huge storage overhead, 16 bytes. Doesn't sound too much, 16 bytes, come on. Someone said in the past 64K, or yes, 640K are enough forever. Just think about that, 16 bytes. 400% overhead compared to an int-identity column. Means we need for that key 400% in our cluster index of overhead and also 400% in every non-cluster. Just think about that. Means the larger your tables are, the larger will be your overhead that you have to carry on with that specific clustered key. So 16 bytes, normally you're saying that's nothing, but that can be a really, really huge overhead when we are talking about larger tables. As we have seen, we have the clustered key always as the lookup value in the leaf level of our non-clustered index when we have defined the non-unique non-clustered index, which is normally the case. We also have that clustered key value in the navigation structure to make the non-unique non-clustered index unique. So we're just polluting our non-clustered index with that clustered key value. And the question is also, are we doing scans by routes? I've never ever seen a business requirement that tells me, please give me back all rows which are starting with the unique identifier value of A to AF. Never seen that. And I've seen crazy things in my life. Never seen that. But I have already seen business requirements like, give me back all sales from the last month. Means when you are sorting, when you are clustering your table on a date column, that can be also very, very interesting. When you're doing range scans on that column, for example, when you are looking on a data warehousing scenario, your fact table is always sorted, clustered on a date column. Because you are querying on date ranges, okay? But we are not really querying on grid ranges. Not really, okay? For example, very simple example regarding the storage overhead. Imagine we have a table with 1 million of records, 6 non-clustered indexes. With an int column as a clustered key, we need around 27 megabytes for the navigation structures of all those indexes. When we're doing the same calculation with a GUID, 16 bytes, we need 107 megabytes, 4 times the space. 4 bytes versus 16 bytes. It's just 4 times the overhead. Just think about that. Performance. Very simple to reproduce. Create a table with an int identity column, create a table with a unique identifier column as primary key, and insert 100,000 records. The int identity table will be faster. Why? Because we have no page splits. We're just inserting at the end of our index. It's the same when you're inserting a new person into a phone book. When you're inserting that person at the end of that phone book, it will be very, very simple. You're just attaching one additional page. When you have to insert that page in the middle of your phone book, it's a little bit more complicated. It's the same here. And even on SSDs, as you can see, you have some overhead. Those are just the CPU cycles, the additional CPU cycles that we need to perform page splits. And as you can see, when you are running on traditional magnetic hard drives, 1 minute versus 150, that's almost 200%. That's the random I/O. Random I/O means we have to reposition our diskette, and that takes time. Introduces latency, introduces slowness in our transactions. And we want to have very, very good performing SQL servers, not bad performing ones. Okay? So really very simple to reproduce. Just create a table, int identity, unique identifier, insert a few thousand records. And you will see it, that the int identity column will be faster. Let's have a look on that. Let's create a new database. And I'm creating here now a very bad table. ID column, unique identifier, primary key. Means SQL Server has created in the background a unique clustered index. So when we go to sys indexes, where object ID equals the object ID of that specific table, you can see we have a clustered index which is unique and is used as primary key. Okay. As I've said earlier, default option here is clustered. Primary key clustered. As we will see later, things are changing completely when we are enforcing the primary key through a unique non-clustered index. The bad thing here is that default is clustered. The default option is clustered means you don't have to specify it. Means you have, normally when you are working with SQL Server, no idea in the first step that the primary key is different as a clustered index. And you have no idea that you can also enforce a primary key constraint through a non-clustered. Because when we see here clustered, maybe we're starting thinking, hey, clustered, maybe we also have a non-clustered option. Okay? So just a bad default choice by SQL Server. I'm inserting 100,000 records. I want to show you something interesting. I'm going to Performance Monitor. Takes a few seconds. And we have here performance counter page splits. So we have here SQL Server, we have access methods, and somewhere we have page splits per second. Who trusts that performance counter? Everyone! It's a Microsoft product. So I'm running that performance monitor trace and we are capturing page splits per second. Of course, we are using a unique identifier as clustered key means we have page splits. Very easy. We're just producing page splits. Because SQL Server has to ensure the sorting order and the leaf level of our clustered index. So as you can see, we have around 50 inserts per second. As you can see, they are also varying a little bit. Those are just the page splits that we are currently performing. So we are finished. When we again check our fragmentation, you can see 99%. Means almost every page is out of order. When we're scanning that table, we're just performing random I/O in our storage. Very, very bad. And creating a table with an int identity as primary key. Very good solution. Again, I'm inserting 100,000 records. And what can we see? We have page splits. We have page splits. But as you can see, those are the good ones. No, we can't see it. Just kidding. You have to know it. But you can't know it from that output. In SQL Server, we are mainly dealing with two specific page splits. Good ones and bad ones. The bad ones are the so-called hard page splits, which we are doing in the middle of our index. And the good ones, the soft page splits, at the end, when we're just appending a new page to our index. The crazy thing about that counter, it just returns both page splits, good and bad ones, so you have no idea if those are good or bad ones. Forget about that performance counter. It's meaningless. It's meaningless. It doesn't tell you anything, even in SQL Server 2014. Microsoft just want to confuse us. Okay? It's a meaningless performance counter.
So the height of peaks mean nothing?
Sorry?
The height means nothing because the peaks are higher on the other graph.
Yes. Here, as you can see, we are constantly inserting around the same amount of records because we have good page splits. Earlier, we had a lot of up and downs because, again, we are performing bad page splits, means we are again introducing some additional CPU cycles, which just takes some time until they are completed. But never ever trust anything. Never ever trust anything. Especially nothing from Microsoft. Okay? When we check our fragmentation, 0.7%. And as you can see, our clustered index has only 2 levels. With only 2 levels. Our clustered index is just smaller. As you can see, we have here a page count of 567. When we go back to our other table with the Uniqueidentifiers clustered key, we have 3 levels with a higher page count. Just think about that. Same amount of records, 100,000. The only thing that I have changed was the clustered key. The column on which we have defined our primary key constraint. Nothing more. Okay? Nothing more. So So here you can see very, very easily that we're just introducing additional overhead. As we have said, we have here the so-called external fragmentation, means logical sorting order versus physical sorting order, and we also have a so-called internal fragmentation, means how full our pages are in the leaf level. When you have an ever-increasing value like an int identity column, you're just inserting at the end new records into your clustered index. Means your pages are almost 100% full. You're just using as many space as possible on that page. That's not possible with a unique identifier. When we look up to our unique identifier, you can see we have an average page space used of 70%. Of course, when you're performing a page split and you're allocating a new page, you insert that record, you have to wait until another record comes in which fits your sorting order so that you can use that space that you have already allocated. Means currently we are using in the leaf level of the clustered index only 70% of our pages. Means when we're doing a scan, we're scanning 30% empty pages, empty space. Means your scan is 30% slower because we're just scanning nothing, no real data. Because we have to wait until we're getting a new value which fits onto that page regarding the sorting order. Means you're wasting 30% in your storage, and you're also wasting 30% in the buffer pool of the memory cache of SQL Server. Therefore, we also have here 3 levels instead of 2 with the int identity column. Just think about that. You are introducing external fragmentation, random I/O, and you are introducing internal fragmentation, means we're just wasting space in the leaf level of our clustered index. Okay. Questions so far?
You said normally it's considered no index as a heap table, but it's argued that a surrogate primary key with an integer value is in effect a heap table. And you had on your slide that it was no heap tables. Is it different in Microsoft SQL?
Well, with the heap tables, you have no clustered index, means you have no physical sorting order. It's just a heap of data, nothing more, which can also introduce different side effects, like forwarding records. Normally, we're just saying we want to have a clustered index on a table, and only in specific scenarios we want to have heap tables. When we need to support a huge insert activity, for example, when you're thinking on logging and outputting tables. Because in a heap table it doesn't matter. You're just inserting a new record, we have no sorting order. It's the same when you're pulling out every page of a phone book, laying in front of you, and you're inserting a new record. You just allocate a new page, put it on top. Doesn't matter where. Very, very fast for insertion, very, very slow for searching data. Means again, you have to balance your read and write activity. It's the same as with indexing. When you add one additional index, you can improve your read performance, but it will degrade your write performance. That's the double-edged sword of indexing. It's the same when we're talking about heap tables and cluster tables. Cluster tables are very, very fast for searching data, slow for insertion, because we have to maintain the sorting order. Heap tables are very, very fast for insertion, very, very slow for reading data. So everything has just advantages and disadvantages. So it mainly depends in SQL Server. Who likes so far primary keys as unique clustered indexes? Nobody. Perfect. So let's talk now how we can still use unique identifiers as primary keys. SQL Server is giving us some options. The first thing that I have already demonstrated, just enforce your primary key as a non-clustered index. And all our problems are just gone. Very simple. Means you have your whole fragmentation, your page splits in a non-clustered index, which is just a supporting index. We're not using that non-clustered. That non-clustered is only used to enforce the uniqueness of that specific column. Means we can cluster, we can sort our table on a different column. So a very simple solution. If you have already a bad database design in production, you can also work with the so-called fill factor. Fill factor means when we are creating a clustered index or when we are rebuilding a clustered index, we are leaving free space in the leaf level of our clustered index. Means when we are inserting a random key value, like a unique identifier, we have some free space. Means we are just inserting the new record without performing page splits. Of course, at some point in time, your leaf level is again 100% full, and afterwards, again, we have page splits. So a fill factor is just a transparent option on the index to lower page splits. We don't need to have any application changes. It's just an option for the database administrator. If we want to enforce the primary key as a non-clustered index, and we have already a table design in production, it's a little bit more complicated. In the first step, we have to take our database offline, because afterwards we have to disable all our foreign keys. As we have already said, when we are dealing with our primary key, we are also dealing indirectly with all our foreign key constraints. When we are disabling our foreign key constraints, we have no referential integrity anymore. Therefore, we are disabling in the first step our database. Means we are currently not supporting any workload. Normally I'm talking here about DBAs. When I have DBAs in front of me, I'm always saying we are disabling our database because we are not trusting our developers. Means when you have a bad written application and that application violates your referential integrity, afterwards you're not able to re-enable your foreign keys anymore. So it really depends how smart your application is. As I've said, normally we are trusting no one on Earth. So just to be sure, take the database offline, disable all foreign keys, disable the non-clustered indexes, and afterwards we drop our primary key constraint. We are dropping our primary key constraint. We can add a new clustered key column, like an int identity column. Maybe we have already a column on which we want to cluster our table, for example, an order date. Also, ever increasing, no page splits. You just have orders in the future at the end of your clustered index. Then we create a clustered index on that new column, and afterwards we create the primary key on the same original column and enforce the primary key as a non-clustered index, as a unique non-clustered index, and afterwards we enable our foreign keys, enable our non-clustered indexes, and finally bring the database online. Normally you will not do that in production because it's just too much work. As I've said, when we are talking about the primary key, you also have to do that on every foreign key column. So it's just pain in the ass. Okay? Let's have a look on that. Let's have in the first step a look on the fill factor. So again, I'm just creating a variable table. Primary key on a unique identifier column. Again, I'm inserting 50,000 records, means now we have bad page splits. Page splits in the middle of the clustered index. Takes a few seconds. Again, when we check the fragmentation of our index, you can see 99% in the leaf level. So again, very, very bad. And our internal fragmentation, 70%, means we have 30% of free space on our data pages in the leaf level. Means when we're inserting again additional records, we have our page splits. So just the traditional behavior of a unique clustered index defined on a unique identifier. What we can do now, we can specify a fill factor. Means we're just rebuilding our clustered index and we're specifying a fill factor. Never ever specify a fill factor of 50%. 50% is only good for demonstration. Means your leaf level is 100% larger. Because we are only using 50% of our data pages in the leaf level. Means when we have random inserts with a random clustered key value, we have space to support that insert without performing page splits. So normally in production, you're lowering down your fill factor maybe 95, 90% and see how your workload reacts. Never ever go down to 50%. So I'm just checking the name, copying that over. What we can also do to see the side effects earlier. I'm enabling the session option set statistics IO1. Set statistics IO1 is telling us how many page reads we need for a specific query. So when we are doing a simple select star against that table, you can see we need 596 logical reads. We're just reading 596 pages in the leaf level of the clustered index. As you have also already seen earlier, we have here those pages, and we have currently a fill factor of 70%. The internal fragmentation is nothing more than the fill factor. Currently we are working with a fill factor of 70%. Means our page splits have produced an internal fragmentation. We are using 70% of the data pages and the other 30% are just empty. Means when we are now rebuilding our clustered index with a fill factor of 50%, we are not getting 2000 pages. Because we have already implicitly a fill factor of 70%. Means when we are rebuilding it, and we check the page count again, you can see, that was the wrong database, sorry. Database ID 1. Earlier we had 500 something, and now we have 845. And you can see our internal fragmentation is 50%. That's the fill factor. That's the fill factor. Means when we afterwards perform a scan, as we have done here, the scan is slower because we need to scan 850 pages instead of 500 something. So again, when we are dealing with the fill factor, we are improving write performance because we don't need page splits at the beginning, and we are degrading read performance. Same problem. Okay? Means with a fill factor of 50%, we can insert now 10,000 records. And guess what? We have no page splits. Makes sense? There's free space in the leaf level of the clustered index. So we are able to perform inserts without producing page splits. Means our external fragmentation, logical sorting order versus physical sorting order stays at 0%. Of course, our internal fragmentation will be not 50% afterwards. It will be around 60%. Because we are just using free space in the leaf level of the clustered index. So we are finished. And as you can see, one database. As you can see, we're around 60%. And our external fragmentation, 0. 0%. Means when we are scanning that table, we're just performing sequential I/O. We're just reading forward in our storage very, very fast. Okay? So when we insert now again 50,000 records, we are again triggering page splits. So when we go up, let's insert around 50,000 records again. Takes some time. Now you will see at the end, again we will have page splits. Again, bad ones in the middle of our index, as you can see here now. Okay? We can scale that. And now we are finished. Means when we are checking the fragmentation again, 66%. Recommendation from Microsoft, more than 30% we built. We've just inserted a few thousand records, we have again 66% fragmentation. And you can also see average page space used is here 66%. So again, we have 1271 pages. When we rebuild our index again with a fill factor of 50% and check the fragmentation again, you can see we have almost no fragmentation, 0.05, and we have 50% internal fragmentation with a page count of 1,700. That's the side effect. When we are scanning now the table, we need the 1,700 page reads. Okay? But as you have seen, the fill factor is just a transparent option on the index. We're not changing our workload in any way. We don't have to do anything. Okay? Questions on that?
So if that ends up, if it's a large table, and that ends up being physical I/O,
Yeah.
the later version is still better even though it's more page reads because they're linear, aren't they?
Yeah.
Not random.
Yeah. Other questions? Good. Let's look on the second option, enforcing a primary key through a unique non-clustered index. As I've said earlier, just specify primary key non-clustered and all our problems are just gone. Very simple to solve that problem. Of course, as you have said earlier, everyone is using primary keys as clustered indexes. So let's create again that bad table and fix it afterwards. So we want to enforce now that primary key constraint as a non-clustered index. By default, the primary key is enforced as a unique clustered index. Let's insert a few thousand records, 10,000. Again, we have our page splits, bad ones. As I've said earlier, if you don't trust yourself, set the database to offline means only the current user can work with that database. What I'm doing in the first step, I'm just copying again the name of the primary key constraint. because when we have the database offline, you can't even access the database through Object Explorer. So let's set it to offline. So nobody else can access that database in the meantime. Maybe we have an application which violates our referential integrity. The next step, we have to disable all our foreign keys, our non-clustered indexes, and finally, we are dropping our primary key constraint. So I'm dropping here the primary key constraint. And now, it depends. You can add a new ever-increasing column, like an int identity column. Maybe you have already a column on which you want to sort to cluster that table, for example, an order date column. I have added here an int identity column, means I have here now an ever-increasing value. And I have here in the first step my random old key value of the unique identifier. So I'm creating my unique clustered index on the new added column or on an existing column like an order date. And I'm adding again my primary key constraint on the original unique identifier column, enforced as non-clustered index, as unique non-clustered index. So from an application perspective, nothing has changed. Our primary key constraint is still on the same column. It's just enforced by a unique non-clustered index in the background. Means we can bring our database online when we have enabled our foreign keys and non-clustered indexes. When we look on both indexes that we have in the correct database, you can see we have our clustered index. We have our non-clustered index for enforcing the primary key constraint. And you can see we have almost no fragmentation in every index. No internal fragmentation, everything is fine. Let's insert 10,000 records. Of course, our clustered index doesn't get any fragmentation because we have clustered our table on the ever-increasing int identity column. Means in the clustered index we have good page splits. At the end our table just grows. And the non-clustered, for enforcing the primary key constraint, has all the page splits and the fragmentation of 99%. But nobody cares about that non-clustered. It's just a supporting index to support and enforce the primary key constraint. Nothing more. As you can see in our clustered index, with a fragmentation of 4.7%. And as I've said, the clustered index, that's our table data. In the leaf level, we have our table. Means when we are scanning that clustered index, we have almost no random I/O in our storage. And you can see our pages are almost at 100% full. Means the fragmentation from the unique identifier is moved to our non-clustered index. Again, with a fragmentation of nearly 100%, and we have an internal fragmentation of 70%. But we are not dealing with that non-clustered. Maybe SQL Server is using that non-clustered when you're searching for a specific grid. Or if we are crazy and performing range scans by grid. But normally when we are accessing our table through scan operations, we are using our clustered index where we have no fragmentation. So we have just moved all the problems from the unique identifier into a non-clustered index. And nobody cares about that non-clustered. Make sense? Questions on that?
There's still use of the non-clustered on write.
Of course, when we are performing write operations, insert, update, delete statements, we have to pay a penalty because we have an additional non-clustered index.
So we're just increasing the
Of course.
load actually by the new cluster.
Yeah, of course. We're just dealing now with two indexes. So with that approach, we are able to love our unique identifier again. Okay?
So all your other non-clustered keys are going to use that.
Clustered key the int identity column as a lookup value, yeah?
Shrink as well.
With all our problems solved. So primary keys as unique identifiers are not really a problem in SQL Server. The only problem is that SQL Server by default creates a unique clustered index for it. So when we create a unique non-clustered index for it, we're just fine with it. Yeah?
What about using sequential IDs?
Also a possibility.
Some of that overcomes the
Yeah, of course, yeah.
fragmentation.
Also no problem. It just should be an ever increasing value so that you are just happening at the end of the clustered index new records. Okay. So we have a few more minutes. And I want to talk now why unique identifiers as clustered key are really awesome. The approach that we have seen so far doesn't scale. Imagine you have a table, a logging auditing table where you're inserting 100,000 records per second. Your ever increasing value as a clustered key will not scale. It will not scale because you are hitting a specific problem. The so-called last page insert latch contention means when we are using an ever increasing value like an int identity column, we have a single hotspot at the end of our index. We're just inserting rows at the end of our index. Internally, SQL Server uses so-called latches to physically protect pages in memory. Means when you want to write to 2 pages in memory, those writes are just serialized, one after one. Because otherwise, one insert will overwrite the information of the other insert. And for that serialization, SQL Server is using so-called latches. Means when we are inserting a record on our last page in our clustered index, we have to exclusively lock that page in memory. Means in the meantime, nobody else can read and write from that page. As a conclusion, we have single-threaded inserts at the end of our clustered index. Means when you have a huge amount of parallel queries, which you're inserting in your logging auditing table, you're just inserting one record after one record. You have single-threaded inserts. This will not scale. Of course, you need a workload which leads to that specific problem. So when you're dealing with normal tables, you will not hit that specific problem. So you are mainly seeing that specific problem when you're dealing with tables where you have a huge amount of insert activity. Traditionally logging auditing tables. So not with traditional tables in our customer databases, order databases.
Sorry, what number approximately does it start getting a problem?
You have to benchmark it. We'll see it very soon. I can even reproduce that on a MacBook Air. So it's very simple. You just need concurrent users, nothing more. As soon as you have concurrent users, you have single-threaded inserts. One user waits on the other one. What are solutions? Use a random clustered key value, like a unique identifier. Just make all the bad things that we have already seen. You can also use a more can also use other options. Of course, a unique identifier is 16 bytes long, so we are again dealing with a huge overhead. Unique identifier is mainly a quick solution, but the goal is to use a random clustered key value. Means we're distributing our inserts across the whole leaf level. So we have not a single hotspot at the end of our clustered index anymore. We're just distributing. Means we're latching multiple pages concurrently exclusively. Means we have concurrent inserts again into our clustered index. Another option is to use hash partitioning. Hash partitioning means you're just partitioning your table on a hash value. Means you are getting internally again different B-tree structures which you can again concurrently access for write activity. Drawback of hash partitioning is you need the enterprise edition of SQL Server. Another option starting with SQL Server 2014 is in-memory OLTP. Hackathon. It's a traditional example where you can get rid of the last page insert latch contention. Okay? Let's have a look on that. I'm creating a simple database. I'm creating a perfect table. Int identity primary key. We all know that's very, very good. But it will not scale. Creating a simple stored procedure where I'm just inserting the 10,000 records. And what I'm doing now, I'm using a tool called ostress.exe. You can download that from Microsoft. And I'm just executing that stored procedure with 100 parallel users, last parameter. Means with 100 parallel users, we have single-threaded inserts at the end of our clustered index. I'm copying that, going over to the command line. And I'm executing that. When we go to activity monitor, takes a few seconds. Takes a few seconds. As you can see, we are running with 100 parallel users. Almost everyone is waiting. Means we just have single-threaded inserts at the end of the clustered index. We can go to the dynamic management view, system always waiting tasks, and restricting on a wait type which starts with page latch. So we are just waiting on latches in memory. Maybe I'm already finished. Yeah. Let's start it again. Yeah. And here you can see 96 sessions users are currently waiting on an exclusive latch. We want to have exclusive access to the last page in our clustered index. And you can see the page ID, 3350. It's the same for every session. We're just accessing single-threaded the last page at the end of our clustered index. Last page insert latch contention. An ever-increasing value like an int identity doesn't scale. Again, advantages, disadvantages. Okay? So just think about that. Even when you are using all those best practices and you are using an int identity as a primary key, this doesn't mean that you have a very good performing SQL server. Again, it depends on your workload. I'm trying to establish here VPN connection. Let's see if that works. And I have access here to a huge machine. 32 cores, Fusion IO storage, 4 terabytes, it's like heaven. almost heaven, 256 gigabytes of RAM. Then running the same demo on that machine. The only thing that I'm changing here, I'm running it with 500 users. And I'm piping everything to null so that we see no output, because the representation of the output takes time. We want to eliminate that time. When we look into the activity monitor, what can we see? Waiting tasks, almost 500. Every user is waiting. Means you can't solve that problem with hardware. The more hardware you have, the larger your problem are. Very simple. So even on a huge machine, everyone is waiting. Single-threaded inserts at the end of the clustered index. It's just a restriction of the B-tree structure. Because, of course, we have to synchronize concurrent access. Means we have to latch those pages. Means when we're changing the page, we have to latch it exclusively. Means nobody else can write and read from that page. It's just a limitation of a data structure, nothing more. It's just a B-tree. Because you have to synchronize multiple concurrent threads. And as you can see, it takes forever. It takes forever. Minutes. We have no minutes, so let's stop that. And I'm running the same thing again with a unique identifier as a primary key, as a clustered key. Whoops. And now you will be very, very amazed. Of course, we have again waiting tasks. We are waiting on our transaction log. So as you can see, we are writing here with almost 900 megabytes per second to the transaction log. As you can see, we have mainly the wait type write log. We're just waiting on our transaction log, nothing more. The transaction log is always our final bottleneck in SQL Server. We're just waiting on our transaction log, means we have completely eliminated that latch contention at the end of our clustered index, and we are already finished. We are already finished with the same workload, because we were able to parallelize the inserts across the whole leaf level of our clustered index. Impressive, isn't it? So you really have to think what you want to get from SQL Server. Not every best practice leads to the best performance. You really have to carefully evaluate every option. When you have tables which have to support a huge insert activity, maybe a random clustered key value is a good idea. Because otherwise, when you are using an ever-increasing value like an int identity column, we have just single-threaded inserts at the end. Okay? Cool. How do you like the session? Cool. So as you can see, the primary key has huge consequences in SQL Server. So what we have seen in the last 90 minutes, we have talked initially about clustered, non-clustered indexes. Most important thing here is the dependency through the clustered index. At least we have the clustered key in the leaf level of the non-clustered. If the non-clustered is a non-unique, non-clustered index, we also have the clustered key in the whole navigation structure, so we are just polluting our non-clustered indexes. Afterwards, we have talked how we can use unique identifiers as primary keys. As we have said, easiest option, enforce the primary key as a non-clustered index, and almost all our problems are done. If you have already database schema in production, we can use the fill factor, or we can also change it on the fly, as we have seen, but it's a very, very hard job to do that because primary key column is a foreign key column in a different table, so it just affects our whole database schema. And finally, I just wanted to show you that even with an ever increasing value like an int identity, you can have performance problems because of that last page insert latch contention where we're just getting a hotspot at the end of our cluster index. Questions? Do you want to have more about that stuff? Do you like it? I'm running in May my SQL Server performance tuning and troubleshooting workshop, 4 days, where I'm talking 4 days long about such things, performance problems in SQL Server, how you can analyze, how you can identify and fix them. So if you're interested, you can find further information on my website, sqlpassion.ad. If you're giving me a business card of yourself, I can also give you a discount of 10%. So thanks for attending. Enjoy the rest of the day and the conference. Thank you.